The desert wind moves across the Giza plateau like a whisper from another age. Sand shifts and settles. The sun drops toward the horizon, painting the Great Pyramid in shades of amber and gold. For a moment, standing in its shadow, you feel small. Not just physically small, though the monument towers 146 meters above you, but temporally small, as if you're standing at the edge of a story so old that even memory has forgotten it. We've been told for generations that this pyramid, the largest and most precise stone structure ever built, was the work of Pharaoh Khufu, a tomb constructed around 2560 BC by tens of thousands of workers using copper tools and determination. The story fits neatly into textbooks. It gives us comfort. It tells us that human ambition, given enough time and sweat, can achieve the impossible. But what if that story is wrong? Not slightly wrong. Not off by a few decades or a different pharaoh. What if the Great Pyramid is thousands of years older than we think? What if it was built by a civilization we've completely forgotten? One that existed before the first Egyptian dynasty, before the first written word, before history itself began. This isn't a story about conspiracy. It's a story about mystery, about the questions that emerge when you look closely at the stones themselves, when you measure the angles with precision instruments, when you ask how Bronze Age people could have achieved what modern engineers struggle to replicate. The pyramid stands there, massive and silent, keeping its secrets. Every year, millions of tourists visit. They take photographs. They listen to tour guides recite the same comfortable narrative. Khufu built this around 2560 BC as his tomb. It took 20 years. Tens of thousands of workers, copper chisels and determination. But some people look closer. They measure. They calculate. They question. And the more they question, the less sense the official story makes. Let's begin where all mysteries begin. With doubt. With a single name painted in red on ancient stone. With a British colonel who desperately needed to make a discovery. With the moment when everything we thought we knew about the pyramid started to crack. Because if the foundation is false, then everything built upon it must be examined again. Every date, every assumption, every comfortable certainty. The stones themselves don't care about our certainties. They simply stand there, waiting. They've been waiting for thousands of years, perhaps tens of thousands of years, waiting for us to ask the right questions. So let's ask them. In 1837, a British military officer named Colonel Richard William Howard Vyse arrived in Egypt with money, ambition, and gunpowder. Egyptology was young then, more treasure hunting than science. Men like Giovanni Belzoni and Giovanni Caviglia had made names for themselves by hauling statues and artifacts back to European museums. They were celebrities, lionized in London drawing rooms, their discoveries making headlines. Vyse wanted the same glory. He craved it. But he had a problem. Other explorers had already claimed the most obvious discoveries. The pyramids had been explored, measured, and written about for centuries. Ancient Greek tourists had visited Giza. Roman emperors had left graffiti. Medieval Arab scholars had written treatises. By the time Vyse arrived, the Great Pyramid seemed picked clean of easy fame. So he did what desperate men do. He got aggressive. Vyse hired more workers than his rivals. He bribed officials. He used his wealth and military connections to push other explorers aside. When the skilled Italian explorer Giovanni Caviglia started making progress at Giza, Vyse simply outspent him and eventually locked him out of the site entirely. Then Vyse started using explosives, In his own journal, Operations Carried On at the Pyramids of Gizeh, published in 1840, Vyse describes how he used gunpowder to blast through sealed passages and chambers. The explosions cracked ancient granite, scattering dust and smoke through corridors that had been silent for millennia. To later archaeologists, this approach bordered on vandalism. To Vyse, it was determination. But after months of destruction, blasting chamber after chamber, tunneling through solid stone, he still had nothing to show. No inscriptions, no treasures, no discovery worthy of fame. His funds were running low. His reputation among fellow explorers was crumbling. Other British gentlemen in Cairo whispered that Vyse was a brute, a destroyer with more money than sense. He was becoming a joke. Then, in late March of 1837, his luck changed, or appeared to. While tunneling upward from the so-called King's Chamber, Vyse's team breached a series of narrow spaces. These relieving chambers had been built to distribute the pyramid's massive weight away from the burial chamber below. They were small, dark, cramped spaces, never meant to be seen or entered. On the granite beams of the highest of these chambers, the one Vyse named Campbell's Chamber after a British diplomat, his men reported finding something extraordinary: faint red painted markings, roughly drawn symbols scattered across the granite like graffiti. Quarry marks, the kind that workers might have scrawled to identify stone blocks during construction. And among them, something even more valuable: a cartouche, the oval name ring that identified a pharaoh. The name read, Khufu. Vyse announced the discovery with triumph. Here, finally, was proof. Direct proof. The Great Pyramid belonged to Khufu, the fourth dynasty, pharaoh the Greeks called Cheops. The mystery was solved. The case was closed. The pyramid had a builder, a date, a purpose. Everything could now be organized neatly in the historical record. Newspapers across Europe celebrated his find. Egyptologists finally had their proof. The Great Pyramid was Khufu's monument, built around 2160 BC during Egypt's Old Kingdom. It was official. Vyse's name entered the history books. He got the fame he craved. Museums welcomed him. Scholars quoted him. His financial backers were satisfied. He had delivered. But from the beginning, a few people noticed something odd. The marks didn't look quite right. Unlike the carved hieroglyphs found in royal tombs, carefully chiseled by skilled scribes, each symbol perfect and precise, these looked rushed, crude even. The paint was uneven, the symbols rough. Some were drawn at awkward angles, as if someone had been painting in a cramped space, unable to see clearly. More troubling, some of the symbols were misspelled. A trained scribe in ancient Egypt wouldn't make such errors. Hieroglyphic writing was sacred. It was the language of the gods, and scribes trained for years to master it. Yet there were mistakes no educated person of that era would make. Strangely, those exact same mistakes appeared in a British hieroglyphic reference book published just a few years earlier. A book that Vyse owned. A book he had consulted and cited in his notes. Then there was the paint itself. The red ochre pigment looked unusually bright for paint that should have been sitting in darkness for 4,000 years. Old paint fades, it cracks, minerals break down. But this paint looked fresh. When scientists later examined photographs of the marks, they noticed something else. The paint sat on top of the quarry marks. The guidelines workers carved into stone to align blocks during construction. That meant the paint was applied after the stones were set in place. If the markings were original from Khufu's time, they should have been applied at the quarry or during construction, then buried under millennia of dust. They shouldn't be sitting on top of everything else, bright and clear. And then there was the strangest detail of all. None of Weiss's assistants mentioned the cartouche in their initial field notes. The men who first entered Campbell's chamber didn't record seeing Khufu's name. The first clear reference to the cartouche appeared only in Weiss's later journal entries, written after he'd dismissed or fallen out with several of his foremen, the very men who'd been with him when the chamber was opened. A pattern began to emerge, not of discovery, but of desperation. Imagine Weiss that night, broke, mocked, overshadowed by more successful explorers, running out of time and money. One stroke of fortune could transform him from a failure into a legend. All he needed was a pharaoh's name, a few painted hieroglyphs copied from a book, applied in the dark with red pigment and a brush, and the course of history would be changed forever. Was it forgery? We cannot say with legal certainty. The evidence is circumstantial. No one witnessed him painting the symbols. No confession exists. But even cautious historians admit the inconsistencies are troubling. The scholar Richard William Howard Weiss Jr., the colonel's own descendant, wrote that his ancestors' accounts were laced with contradictions. He didn't accuse his forefather of fraud, but he acknowledged that questions remained unanswered. Egyptologists rarely discuss this publicly. The foundation of an entire chronology depends on those red marks being genuine. Every textbook, every museum placard, every documentary about ancient Egypt assumes that Weiss's discovery was real. Because if it's not, if the name Khufu in the pyramid is a Victorian fabrication, then the monument becomes undated. It could belong to Khufu's era, or it could be far, far older. And that opens a door no one in orthodox archaeology wants to walk through. A door that leads back into an age before Egypt, before dynasties, before recorded history, an age we've forgotten. The entire timeline of ancient Egypt leans on a few centimeters of red pigment discovered by a man using dynamite in a desperate rush for fame. If those marks are younger than the pyramid itself, then every date that depends on them begins to drift backward into an era we do not remember. And so the name in red paint, meant to close the case, becomes the beginning of a new one. In 1984, a team led by Egyptologist Mark Lehner undertook a radiocarbon study of the pyramid's mortar. This was going to settle things. Science would provide an answer. The technique was sound. Radiocarbon dating measures the decay of carbon-14 in once living material. Tiny remnants of straw, charcoal, or plant fiber get mixed into ancient lime plaster as binder. You extract samples, measure how much carbon-14 has decayed, and calculate when that organic material died. The team collected samples from various locations throughout the pyramid. They sent them to laboratories. They waited for the results. When the data came back, published in Archaeology magazine, it seemed to confirm the orthodox view. Most dates clustered around 2500 BC, conveniently matching Khufu's supposed reign. Egyptologists celebrated. The Great Pyramid, they announced, had finally been scientifically dated. The argument was over. Science had spoken. Case closed. But a closer reading of the actual data tells another story. The samples varied wildly. Some differed by as much as 380 years from the average. One fragment even dated closer to 3000 BC, centuries before Khufu's dynasty, before the pyramid was supposedly even conceived. The team attributed these discrepancies to old wood, organic material reused from earlier generations. Ancient Egyptians, they explained, might have burned timber from older structures or used wood that had been sitting around for decades or centuries. That explanation, while tidy, glosses over a deeper problem. It assumes what it's trying to prove. If these echoes of a forgotten era have sparked a flame in your mind, I invite you to join our growing community of seekers. Tell me, as you listen to the desert wind tonight, which city are you in? And what does the clock say in the quiet of your room? If the pyramid's date is already known, then data that doesn't match must be contamination or old wood. If it doesn't fit, it's dismissed. But what if the assumption itself is wrong? What if some of that mortar really is older than Khufu? The scientific reality is messier than the press releases suggested. Mortar represents not original construction, but maintenance. Over time, millennia, the Great Pyramid has been repaired repeatedly. Pharaohs of later dynasties restored it. Priests maintained it. Medieval Arabs removed casing stones. Modern restorers patched damage. Each era left its mark. What the 1984 study actually measured could have been anything. Patchwork repairs from the Old Kingdom, material inserted during Middle Kingdom restoration, medieval cement, modern conservation work. Carbon-14 doesn't tell us when the stone was laid. It only tells us when the last living fragment mixed into its mortar died. To put it simply, dating the mortar is like dating the dust on your bookshelf and calling it the age of your house. Later studies deepened the confusion. In the 1990s, researchers from the University of Zurich reanalyzed similar samples, this time using more refined techniques. Again, they found broad discrepancies, as much as 1,000 years separating different samples. A few pieces even predated the entire Egyptian civilization as we know it, pushing back before 3100 BC, before Narmer unified Upper and Lower Egypt, before the First Dynasty. The researchers were puzzled. They published their findings cautiously, noting the anomalies but offering no definitive explanation. When independent researchers requested new samples to test with even more advanced methods, access was abruptly denied. Official statements cited preservation concerns. The pyramid, they said, must not be damaged further. Unofficially, no one wanted more anomalies, more contradictions, more questions without comfortable answers. Then, in 2020, something remarkable happened. An accident in a Scottish museum changed everything. Abir El-Adani, a curatorial assistant at the University of Aberdeen, was cataloguing old donations stored in the university's collections. Boxes and crates that had been sitting forgotten for decades. Most contained pottery fragments, small statues, the usual archaeological odds and ends. Then she found a small cigar box wrapped in a 1946 newspaper. Inside lay a splinter of cedar wood, dark and dry, carved into a rod-like shape. A faded label read, "From the Great Pyramid, Dixon Relics." El-Adani's heart raced. She knew what this was. In 1872, British engineer Wayneman Dixon had explored one of the pyramid's mysterious narrow shafts, channels barely wide enough for a man to crawl through, leading from the Queen's Chamber toward the outer face of the pyramid. Inside one shaft, Dixon discovered 3 small objects: a granite ball, a bronze hook, and a fragment of cedar wood. The ball and hook ended up in the British Museum, where they remain today. But the wooden piece vanished. For more than a century, no one knew where it had gone. Scholars assumed it was lost, destroyed, or mislabeled somewhere in museum storage. And here it was, in a cigar box, in Scotland. El-Adani immediately recognized its importance. This wasn't just any artifact. This was the only organic material ever found inside the Great Pyramid's original sealed structure. Not in mortar, not in later repairs, but inside the monument itself, placed there during construction or shortly after. She arranged for radiocarbon dating. The sample was sent to laboratories, tested, retested to confirm. The results stunned everyone. 3,341 to 3,094 BC. That makes the wood 5 to 8 centuries older than Khufu's lifetime. Older even than Egypt's first recognized pharaohs. Older than the beginning of dynastic Egypt as we know it. The explanations came quickly, as they always do when evidence contradicts accepted history. Some scholars claim cedar trees could live for centuries. The wood might have been ancient when it was cut and used. Trees growing for 500 years weren't unheard of. But cedar doesn't grow in Egypt. It had to be imported from Lebanon, where ancient cedar forests supplied timber to Egypt for millennia. And while cedars can live long lives, using 500-year-old wood for a small rod seems unlikely. Ancient builders typically used fresh timber, which is easier to work and less prone to splitting. Others argued contamination. Perhaps the wood had absorbed carbon from its environment, skewing the date. But the sample was tested multiple times using modern protocols designed to detect and eliminate contamination. The date held firm. Still others suggested the wood might have been reused from an even older structure. Perhaps Khufu's builders salvaged timber from monuments built centuries earlier. But that explanation raises its own questions. If they reused wood from structures built 500 years before Khufu, what were those structures? Where are they? And why would builders of humanity's greatest monument use old, weathered wood for such a small but important artifact? The simplest explanation, the one that makes fewest assumptions, is that the wood dates to when it was placed in the pyramid. And if so, that means the pyramid's construction began at least 500 years before Khufu was born. 500 years. Half a millennium. That's not a small discrepancy. That's not an error margin or contamination. That's a different age entirely. The fact remains, this is the only direct organic artifact found inside the Great Pyramid's sealed structure, and it places the monument's material at least 5 centuries before its supposed builder was born. One splinter of wood, forgotten in a cigar box for 74 years, could rewrite history, or more accurately, restore a version we've forgotten. Because if the Great Pyramid is older than Khufu, then it's older than the entire dynastic period of Egypt. It belongs to a time before pharaohs, before hieroglyphs, before the civilization we call Egyptian even existed. It belongs to an age we've lost. Stand at the base of the Great Pyramid on a clear morning. Run your hand along the limestone blocks that form its lower courses. The surface feels rough, weathered, ancient. The stone has texture, like old skin marked by time. But weathered by what? Egypt is a desert. It has been for thousands of years. The land of sand and sun, where rain falls perhaps once or twice a year, in brief, insignificant showers. The Sahara stretches in every direction, one of the driest places on Earth. Yet the erosion patterns on the pyramid's lower courses tell a different story. They show something strange, something that shouldn't be there. Deep vertical channels carved into the stone. Grooves that run downward, following the path water would take. The kind of weathering created by rainfall, not wind-blown sand. In the early 1990s, Dr. Robert Schoch, a geologist from Boston University, examined these patterns closely. Schoch wasn't an Egyptologist. He was a scientist who studied rock, erosion, weathering, how stone degrades over time under different conditions. What he saw at Giza troubled him. The erosion patterns didn't match Egypt's current climate. Wind erosion creates horizontal striations, smooth surfaces worn by millennia of sand blasting across stone. But the Great Pyramid's lower courses showed vertical channels, water-cut grooves, the unmistakable signature of heavy rainfall over long periods. Schoch consulted climate data. When was the last time the Giza Plateau experienced sustained heavy rainfall? The answer? Thousands of years before Khufu's time. The Sahara hasn't always been a desert. Climate records reconstructed from sediment cores, pollen samples, and ancient lake beds reveal that North Africa went through a dramatic transformation. During the early Holocene period, roughly 9,000 to 5,000 BC, the Sahara was green. Grasslands stretched across the region. Rivers flowed. Lakes dotted the landscape. Rain fell regularly. Ancient rock art in the central Sahara shows giraffes, elephants, hippos, animals that require water and vegetation. These weren't fantasies. They were records of a time when the desert bloomed. Then, around 5000 BC, the climate shifted. The African monsoon pattern changed. Rain decreased. Vegetation died. Rivers dried up. The Sahara transformed from savanna to desert over the course of several centuries. If Schoch was right, the erosion on the Great Pyramid's base dated from before that transformation, from the Green Sahara, from an era when rain fell regularly on the Giza Plateau. That would mean the pyramid's lower courses were exposed to weather thousands of years before Khufu's reign, long before Egypt's dynastic period began. When Schoch presented his findings at the Geological Society of America in 1991, the response was explosive. Egyptologists attacked him immediately. He was a geologist, they said, not trained in Egyptian history or archaeology. He didn't understand context, chronology, or the established facts. They pointed to alternative explanations. Wind erosion, sand abrasion, damage from modern pollution, even water seepage from the ground. But Schoch stood by his observations. Wind creates horizontal patterns. Water creates vertical ones. The channels on the pyramid run vertically, consistent with rainfall runoff, not sandblasting. He wasn't alone in his observations. The Sphinx, located just a few hundred meters from the Great Pyramid, shows even more dramatic water erosion. The Sphinx sits in a rectangular enclosure carved from the limestone bedrock. The walls of this enclosure are deeply weathered, showing the same vertical channeling, the same rounded profiles created by water. Egyptologists claim the Sphinx was built during the reign of Khafra, around 2500 BC, roughly the same time as the second pyramid at Giza. But the erosion on the Sphinx enclosure suggests exposure to far more water than Egypt has received in the past 4,500 years. Schoch performed stratigraphic analysis, comparing the Sphinx erosion to other limestone structures in Egypt. Tombs and temples from the same supposed era, the Old Kingdom, show minimal weathering, nothing like the deep grooves carved into the Sphinx enclosure. If everything was built around the same time and exposed to the same climate, why does the Sphinx look thousands of years older? Schoch's estimate, the erosion occurred between 9,000 and 7,000 BC, an age consistent with the end of the last ice age, when North Africa experienced its final period of sustained heavy rainfall before the Sahara dried out. If that's accurate, the Sphinx and the Great Pyramid belong not to Khufu's Egypt, but to an earlier world. a world that disappeared when the climate changed and the desert swallowed the grasslands. Other geological evidence supports this timeline. Sediment cores from the Nile Valley reveal high flood layers dating back more than 7,000 years, when the region was far wetter. Ancient lake beds in the western desert contain fossils of fish, crocodiles, and water plants that died out when the rain stopped. Climate models show that the African humid period, as scientists call it, ended abruptly. The transition from green Sahara to desert happened over just a few centuries. Civilizations that depended on those grasslands and water sources would have had to migrate or disappear. Perhaps some of them migrated to the Nile Valley, one of the few places in North Africa where water remained reliable. Perhaps they brought knowledge with them. Skills in astronomy, mathematics, and construction. Perhaps they built monuments on the Giza Plateau during that earlier, wetter time. Beneath the sand around the pyramids, archaeologists have found something else curious. Limestone pavement so heavily eroded it suggests exposure to rainfall long vanished from the region's climate record. The pavement surrounds the pyramids and the Sphinx, forming a kind of plaza or courtyard. The stone has been worn smooth in some places, deeply pitted in others, showing the characteristic patterns of water pooling and running off. This isn't the light weathering you'd expect from 4,500 years of occasional rain showers. This is deep erosion requiring sustained precipitation over long periods. Nature, it seems, carved its own timestamp into the stone, a geological clock that tells a different story than the historical one we've chosen not to read, or perhaps one we haven't wanted to read, because accepting it would mean rewriting everything we thought we knew about the origins of civilization. Let's talk about numbers. Numbers don't lie. Numbers don't care about theories or traditions or what we want to believe. Numbers just are. The Great Pyramid contains approximately 2.3 million stone blocks. That's not an estimate. That's a count based on careful measurement and calculation. Each block averages 2.5 tons. Some are smaller, some are larger. The granite beams in the King's Chamber weigh up to 80 tons each. The total weight of the entire structure, approximately 6.5 million tons. According to mainstream history, this monument was built in 20 years during the reign of Pharaoh Khufu, roughly between 2580 and 2560 BC. 20 years. Let's break that down. 2.3 million blocks divided by 20 years equals 115,000 blocks per year. 115,000 blocks per year divided by 365 days equals 315 blocks per day. 315 blocks per day divided by 24 hours equals 13 blocks per hour. One block every 4.5 minutes. Every 4.5 minutes, working 24 hours a day, every single day, for 2 decades straight, workers would have had to quarry a 2.5-ton block of limestone, transport it to the site, lift it into place, and fit it precisely with its neighbors. No breaks, no holidays, no stopping for weather or festivals or the death of a pharaoh. Just constant, relentless work. And that's assuming everything went perfectly. No blocks broke during quarrying. No tools failed. No workers got injured. No mistakes were made that required rework. Even with modern cranes, bulldozers, and laser-guided equipment, no construction project of this scale has achieved such speed and precision. The Burj Khalifa in Dubai, the world's tallest building, took 6 years to construct using modern technology. Thousands of workers, steel, concrete, computers, and hydraulic machinery. And it weighs far less than the Great Pyramid. Now imagine doing it with copper tools. This is where the official story becomes truly problematic. Copper measures 3 on the Mohs hardness scale. It's a soft metal, useful for making jewelry, wires, decorative objects. Not so useful for cutting stone. Limestone ranges from 3 to 4 on the Mohs scale, about the same hardness as copper. You can cut limestone with copper tools, but it's difficult, slow work. The tools wear out quickly, dulling and bending with each strike. But granite is different. Granite measures 6 to 7 on the Mohs scale. It's hard, very hard, composed of quartz, feldspar, and mica, all crystalline minerals that resist cutting. In laboratory tests, copper chisels barely scratch granite before bending. They simply can't cut it effectively. It's like trying to carve steel with a butter knife. Yet the Great Pyramid contains hundreds of granite blocks, massive beams, lintels. The entire King's Chamber is lined with granite, including the ceiling formed by 9 enormous beams, each weighing approximately 50 tons. In the 1990s, experimental archaeologist Dennis Stocks attempted to replicate ancient cutting techniques. He assembled a team, gathered copper tools manufactured to ancient Egyptian specifications, and set to work on limestone blocks. After hours of hammering, sawing, and chiseling, his team managed to cut a few millimeters into the stone. The tools wore out faster than they cut. Chisels bent, blades dulled. Progress was agonizingly slow. And that was limestone, the softer stone. When they tried working granite with copper tools, the experiment essentially failed. The tools couldn't make effective cuts. They could scratch the surface, create shallow marks, but actually shape granite blocks? Impossible. To create just one of those 80-ton granite beams using copper chisels would require thousands of tools, constant reforging of bent blades, and months, perhaps years, of labor per block. Multiply that by hundreds of granite pieces throughout the pyramid, and the logistics become absurd. The standard explanation suggests ancient Egyptians used dolerite pounding stones to chip away at granite surfaces. Dolerite is harder than granite, measuring about 7 on the Mohs scale, so theoretically it could be used to gradually wear down granite through repeated pounding. But anyone who's tried this, and researchers have, knows it's brutally inefficient. Pounding creates rough, uneven surfaces. It shatters stone unpredictably, and dolerite itself is brittle. The pounding stones crack and break apart with heavy use. Yet photographs of ancient quarries at Aswan, where the pyramid's granite was sourced, show something entirely different. Smooth circular drill holes descending deep into solid granite. Straight, precise tool marks. Grooves that run in perfect lines as if cut by machinery. When engineers studied these marks under magnification, they discovered spiral striations, the signature of a rotating tool, like a drill bit spinning at high speed. The grooves descend in continuous helical patterns, exactly like what modern drilling produces. This isn't pounding, this is cutting. Christopher Dunn, a precision manufacturing expert who spent decades working in aerospace and engineering, analyzed these ancient tool marks extensively. He created computer models, measured angles, calculated speeds. His conclusion shocked him. The feed rate, how fast the tool cut through solid granite, was equivalent to a modern drill spinning at thousands of revolutions per minute, applying pressure far beyond what human hands could manage. In modern industry, similar marks appear only on materials shaped by diamond-tipped tools or ultrasonic cutting equipment. Technologies developed in the 20th century. How did Bronze Age builders achieve this? The transportation problem adds another impossible layer. Some of those granite beams weigh 80 tons. They were quarried in Aswan, over 800 kilometers south of Giza. How were they moved? The Nile River would have offered a natural transportation route. Building wooden barges to float stones downstream makes sense. And, indeed, ancient Egyptian art shows boats carrying obelisks and large blocks. But physics intervenes here too. The buoyant limit of a wooden barge, no matter how well designed, has maximum capacity. Load it beyond that point and it sinks. An 80-ton granite block would require an enormous vessel, and even then, balancing such weight on a wooden boat without it breaking apart or capsizing would be extraordinarily difficult. In the 1990s, modern naval engineers attempted to recreate such a barge using ancient Egyptian shipbuilding techniques. They designed it carefully, using the best available wood, following historical ship designs found in Egyptian art. The moment they loaded it with a 60-ton granite block, the vessel cracked and began taking on water. It didn't sink immediately, but it was clear the design couldn't safely transport the heaviest stones used in the pyramid. And even if they somehow managed to float stones down the Nile, how were they hauled from the riverbank up to the Giza Plateau? The plateau sits roughly 60 meters above the Nile floodplain. That's a significant climb. With an 80-ton load, orthodoxy proposes ramps. Giant ramps built of mud brick or limestone rubble, sloping gradually up to allow workers to drag stones using ropes and wooden sledges. But here's the problem. To achieve a gentle enough slope for dragging multi-ton blocks, such a ramp would need to be over 1 kilometer long, and it would contain more material than the pyramid itself. Not a single trace of such a ramp survives. No foundations, no spoil heaps where it was dismantled, no massive quarries of clay or rubble anywhere near Giza. Some researchers suggest a spiral ramp wrapping around the pyramid's exterior as it rises. That would require less total material than a straight ramp. But this too fails under scrutiny. A ramp curling around the pyramid would obscure the builder's sightlines, making precise corner alignment impossible. How do you ensure each level is perfectly flat and square when half your structure is hidden behind a massive earthen ramp? It would also require removing millions of tons of debris once construction ended, work for which no evidence exists anywhere. In 1978, Nippon Television Corporation of Japan, working with Egypt's Supreme Council of Antiquities, set out to test these theories. They attempted to build a miniature replica of the Great Pyramid, using only materials and techniques supposedly available to ancient Egyptians. Their pyramid would stand just 20 meters tall, a fraction of the original. The project became a disaster. Copper chisels failed to shape even small limestone blocks effectively. Tools broke. Blades bent. Progress was impossibly slow. Ropes snapped under the weight of blocks being dragged. Workers couldn't move stones across sand without massive friction, so they poured water to reduce resistance, an ancient technique shown in Egyptian art. But even then, the sledges bogged down. Stones got stuck. Moving just a few dozen blocks took days. Eventually, frustrated and behind schedule, the team resorted to modern steel tools and diesel-powered cranes just to lift the smaller blocks into position. Even with these modern compromises, their pyramid reached only 10 meters tall, half their target, before the project was abandoned. The conclusion, quietly noted in their final report: no known ancient technique could account for the precision or scale of the Great Pyramid's construction using the technology supposedly available in 2500 BC To match the precision of Giza today, engineers would need laser alignment systems, GPS calibration, and hydraulic cranes capable of lifting 100 tons. Yet according to mainstream history, Bronze Age builders accomplished this with nothing more than rope, wood, copper chisels, and human muscle. The numbers don't add up. The physics doesn't work. The timeline is impossible. Something is wrong with the story we've been told. When 19th century surveyor Sir Flinders Petrie arrived at Giza with his precision instruments, he expected to find what everyone expected to find: rough ancient construction, admirable for its time, but obviously primitive by Victorian standards. Petrie was one of the most meticulous field scientists of his era. He brought theodolites, measuring chains, spirit levels, the finest surveying equipment money could buy. He was prepared to measure the pyramid to tolerances of a few centimeters, which he assumed would be more than adequate for ancient stonework. What he found astonished him and troubled him. The base of the Great Pyramid covers more than 13 acres. It's enormous. Yet the height difference between its corners, the variation in level across that vast area, is less than 2 centimeters. 2 centimeters. Across 13 acres. That's not just impressive. That's almost impossible. The 4 sides of the Great Pyramid measure 234 meters at the base. The difference in length between the longest and shortest sides is less than 2 centimeters. Less than 2 centimeters of variation across a structure covering 13 acres. Modern high-rise construction using laser levels and computer-aided design typically achieves tolerances of about 5 centimeters for projects of this scale. The Great Pyramid, supposedly built with rope and wooden tools, is more than twice as accurate. But the precision doesn't stop there. The structure's orientation to true north deviates by just 3 arc minutes. That's 3/60ths of a single degree. A deviation so small it's almost negligible. Even the Hubble Space Telescope, built with computers and precision machinery, has manufacturing tolerances in the same range. How does a Bronze Age civilization achieve accuracy rivaling modern aerospace engineering? Petrie measured everything. He spent months at Giza, crawling over every surface, recording every dimension. His published results, the pyramids and temples of Gizeh, remain one of the most detailed surveys ever conducted. And the more he measured, the more disturbed he became. The casing stones that once covered the pyramid, most now removed, but some still visible at the base, were cut so precisely that the joints between them measure less than 0.5 millimeter. You literally cannot slide a piece of paper between the blocks. Modern stonemasons struggle to achieve such tight fits. It requires machine tools, precision grinding, and careful measurement. Still, there were thousands of blocks, each weighing multiple tons, fitted together with gaps smaller than a credit card. The surface of these casing stones was polished to optical flatness. Petrie ran his hands across them and found them smooth as glass, reflecting light like mirrors. Ancient Greek and Roman writers described the pyramid as gleaming white in the sunlight, visible for miles across the desert, its polished surface so bright it hurt to look at. Creating that finish on limestone requires not just skill, but technology. You need abrasives, polishing compounds, and tools capable of working the surface uniformly across vast areas. Modern restoration efforts using power tools and industrial polishing compounds have failed to match the original finish. In the 1990s, engineers from the French Institute for Research in Engineering and Construction studied surviving casing blocks. They brought precision measuring equipment, micrometers, laser scanners. Their report concluded that the blocks showed tolerances comparable to precision machine metal. One engineer described it as the accuracy of an airplane wing applied to millions of tons of rock. But perhaps most remarkable are the foundation stones beneath the visible pyramid. Ground-penetrating radar reveals interlocking bedrock terraces engineered to distribute weight evenly across the plateau. The result? After thousands of years of earthquakes, sandstorms, and temperature swings, the pyramid has settled less than 2 centimeters. Its structure remains essentially unchanged. To achieve that stability, the builders had to understand load distribution and material expansion coefficients, concepts formalized only in the last few centuries. Inside, the precision continues. The Grand Gallery, a 47-meter passage rising toward the King's Chamber, is constructed of granite blocks, fitted so tightly that air cannot pass between them. The slope of the gallery, 26 degrees, matches exactly the angle of the pyramid's outer face, suggesting intentional harmonic design. The gallery's corbelled ceiling, where each course projects a few centimeters inward, reduces structural stress with mathematical efficiency. This cantilevering technique wasn't rediscovered in Western engineering until the 19th century. The King's Chamber itself is a rectangle with proportions that define harmonic relationships. 10 cubits wide, 20 long, 11 high. The dimensions create what's called a double square rectangle, a ratio that generates the frequencies associated with musical harmony. When sound is produced inside this chamber, the granite resonates at specific frequencies: 440 Hz, modern concert pitch, and 432 Hz, sometimes called natural tuning. The chamber acts as a resonator, amplifying sound at precise wavelengths. This isn't accidental. Ancient Egyptian temples throughout the Nile Valley, at Abydos, Dendera, Karnak, exhibit similar resonant geometries. Stone-carved halls amplify specific frequencies, sometimes causing entire structures to vibrate like tuned instruments. The pyramid's designers understood that form and frequency are connected. That geometry shapes sound. That sound affects consciousness. Then there are the tool marks themselves, tiny signatures carved into the stone. On the granite beams of the King's Chamber lie spiral striations consistent with mechanical drilling. Engineer Christopher Dunn, a master machinist, measured these grooves with precision calipers and found them uniform in pitch. The cutting head advanced at a fixed rate, as though driven by a lathe or rotary drill operating at thousands of revolutions per minute. Laboratory tests using copper tubes and sand, the method orthodox archaeology claims was used, failed to reproduce those patterns. The experiments left rough, irregular scratches, nothing like the clean, concentric rings visible on the ancient stone. At Abydos, granite boxes cut from single pieces of stone show interior angles meeting at perfect right angles, verified with modern laser alignment tools. Their surfaces are flat to within 1/10,000th of an inch, a standard used today in aerospace manufacturing. Yet these artifacts are attributed to dynasties that supposedly lacked iron tools or advanced measuring instruments. To dismiss these anomalies as coincidence ignores the sheer consistency of precision across the entire site. Every block, every angle, every dimension follows the same standard of excellence, as if the builders were working from a unified design code, enforced with machine-like discipline. The pyramid wasn't just built, it was engineered. Under the desert moon, the Great Pyramid seems less a monument than an equation, a vast formula carved into the earth. For those who study it closely, the stones begin to speak a language not of hieroglyphs, but of numbers, mathematics, the geometry of the cosmos itself. Let's begin with a simple but astonishing fact. When you take the perimeter of the pyramid's base and divide it by twice its height, you get 3.1416, the value of pi, accurate to 4 decimal places. Pi, the same constant that defines the relationship between a circle's circumference and its diameter, embedded perfectly in a structure made of straight lines and flat planes. But how could Bronze Age builders have known pi so precisely? The earliest written approximation of pi, found in the Rhind mathematical papyrus, dates to around 1650 BC, a full 1,000 years after Khufu's supposed reign. And even then, it was only an estimate, 3.16. Yet the Great Pyramid, built long before that text, encodes the true value within its geometry. Pi isn't the only constant hidden in the stones. The pyramid also embodies the golden ratio, phi, 1.618. The same proportion is found in spirals of shells, petals of flowers, arms of galaxies. When you divide the slant height of the pyramid by half its base, the result is precisely phi. The structure fuses pi and phi, the mathematics of circle and line, infinity and form. To ancient builders, this wasn't merely clever geometry, it was theology in stone. The union of heaven and earth expressed through proportion. Satellite measurements have shown these ratios recur throughout the Giza complex. The smaller pyramids of Khafra and Menkaure follow similar harmonic relationships, scaled as if by musical intervals. The alignment complements the geometry with uncanny precision. The monument was laid out not as isolated buildings, but as a harmonic system, a mathematical symphony frozen in stone. The pyramid's latitude adds another layer of mystery. 29,997,92458 degrees north, a number that almost exactly matches the speed of light in meters per second. 299,792,458. The precision is uncanny, a match to the 6th decimal place. Skeptics point out that the metric system didn't exist in antiquity. True, but the alignment remains curious because latitude is a function of Earth itself, not human measurement systems. Whether coincidence or evidence of ancient knowledge of physics, it adds to the pyramid's cosmic precision. The monument is also oriented to true north with staggering accuracy, off by less than 3 arc minutes. That's almost 1/20th of a degree. To achieve that, the builders would have needed methods to measure precessional drift, the slow wobble of Earth's axis that changes the position of the celestial pole over millennia. Yet precession wasn't scientifically recognized until Hipparchus of Greece discovered it in 130 BC, more than 2,000 years later. Even stranger, the pyramid's 4 sides are subtly concave, bowed inward by an average of 37 inches. This feature is invisible from the ground, only discernible from the air, as first noticed during a 1940 Royal Air Force survey. The concavity precisely matches the curvature of Earth's surface at Giza's latitude. In effect, the pyramid models both the shape and scale of the planet, implying an understanding of Earth as a sphere, knowledge not formally proven until Eratosthenes in 240 BC, more than 2,000 years after Khufu. Inside, the mathematical language continues. The dimensions of the king's chamber, 10 cubits wide, 20 long, 11 high, form a perfect double square rectangle. This ratio generates frequencies associated with musical harmony, The same harmony exists on a planetary scale. Multiply the pyramid's height by 43,200 and you get 657,000 meters, the polar radius of Earth. Multiply its base perimeter by the same number and you get 40,300,000 meters, the planet's equatorial circumference. The odds of such precision by chance are astronomical. The number 43,200 is itself significant. It's a multiple of 86,400, the number of seconds in a day. It encodes not just the size of Earth, but the rhythm of its rotation. Whoever designed the pyramid didn't simply build a monument. They built a scale model of our planet. To achieve this, they must have known both Earth's circumference and its spherical nature. Discoveries attributed to Greek scholars more than 2,000 years later. Did ancient Egyptians independently calculate these measurements, or did they inherit knowledge from a culture far older? The pyramid's geometry also encodes celestial cycles. The angle of its sides, 51 degrees 50 minutes, mirrors Earth's orbital tilt. Its alignment with Orion's belt and the star Sirius reflects the sky visible around 10,500 BC, long before Egypt's dynasties began. The builders weren't simply observing stars. They were documenting time on a scale of millennia, freezing the heavens in stone. When night falls over the Giza Plateau, the desert becomes an ocean of darkness beneath an ocean of stars. From this height, the sky seems close enough to touch. The Great Pyramid's apex points upward like a compass needle. And suddenly, you begin to understand. This complex wasn't built merely for Earth. It was built for the heavens. If the mystery of the first time has resonated with you, and if you want to continue uncovering the hidden chapters of our human story, please consider hitting the subscribe button. By joining us, you ensure that these explorations continue, and you'll be there when we finally unlock the next chamber of our past.